Hello and welcome to SigmaXL video tutorials. This is part 2 of the video series, Basic Taguchi Design of Experiments Templates. In this video, we'll be covering 2 template examples. The first one will be Taguchi L8 2-level 4-factor Catapult example, and the second, Taguchi L9 3-level 4-factor Paper Airplane example. This Catapult experiment is adapted from the article, The Catapult Problem, Enhanced Engineering Model Using Experimental Design, by Schubert and others, Quality Engineering. To view a completed Taguchi design of the Catapult example, click SigmaXL, Help, Template Examples, Taguchi Examples, L8 4-factor Catapult. If you wish to start a blank template and populate the values like we will be doing in this video, click SigmaXL, Design of Experiments, Basic Taguchi DOE Templates, Taguchi L8 2-level, 4-factor with alias 2A interactions. The response is distance in inches with a target of 50. The goal is to hit a specific target of 50 inches with minimum variation, so we will maximize the signal-to-noise ratio, SN nominal is best, MSD with target, selected from the list as shown. To set our mean squared deviation target value, enter 50 in the MSD target field. If target equals 0, nominal is best, MSD with target, is equivalent to smaller is better. For use on MSD and SN ratio, see the book, A Primer on the Taguchi Method. The inner array controllable factors used in the study are hook, bottom and top, arm length, short and long, start angle, 150 degrees and 177 degrees, and stop angle, hole 4 and hole 5. Select these alias interactions using the drop-down list. Process knowledge, engineering or theory are used to make the selection and assume that the chosen interaction is dominant and the others are negligible. Aliased interactions are often associated with the largest main effects. Confirmation runs should always be used to validate the model. In this study, engineering knowledge was used to select all interactions that included the stop angle. A randomized run order is not given in the paper, so we will be using the default. The 3 outer arrays to be used, yrep1 through yrep3, will be repeat shots fired. The outer array distance values are entered as shown. Scroll to the right to view the calculated statistics. We will focus our analysis on the signal-to-noise ratio, nominal is best, MSD with target. Since this design includes interactions, we will look at the Pareto of ANOVA sum of squares % contribution for signal-to-noise ratios. Scroll right and down to view. Here we see that the hook position and the arm length stop angle interaction are the dominant factors. Scroll down to view the main effects plot for signal-to-noise ratios. I'll adjust the y-axis to get a better scale. With the negative signal-to-noise values, the default x-axis labels appear as on top. To change the x-axis location to bottom, double-click on the x-axis to open Excel Format Axis dialog, and click Axis Options, Label, and set label position to low. We can see that setting hook to bottom and start angle equals 177 maximizes the signal-to-noise ratio. We will use the interaction plot to determine the optimum settings for arm length and stop angle. Scroll down to view the interaction plot for signal-to-noise ratios for the arm length stop angle interaction. I'll adjust my X and Y axis for better visibility. Here we can clearly see the large effect due to the two-way interaction. The effect that arm length has on distance depends on what the stop angle is. The maximum signal-to-noise ratio is achieved with arm length equals long and stop angle equals whole 4. If desired, the interaction plot x-axis legend factors may be switched by clicking on the chart, then selecting Excel, Design, Switch Row, Column. From these plots, we conclude that the optimum setting to produce a maximum signal-to-noise ratio for a distance of 50 inches are as follows. Hook equals bottom, arm length equals long, start angle equals 177 degrees, and stop angle equals whole 4. Had we not considered the arm length stop angle interaction, we would have selected arm length equals short. But this would not have given us a maximum SN ratio. Scroll up and left to enter these values into the predicted output calculator. Factor settings can be selected from the drop-down list as shown. This gives the predicted mean, standard deviation, and signal-to-noise ratio for distance, and agrees with the results given in the paper. The predicted value of 52.9 inches is slightly off the target of 50 inches due to the discrete settings of the categorical factors. Excel Solver cannot be used with this calculator to perform optimization. See the SigmaXL workbook for use of multiple regression in Solver, where we treat the start angle as continuous rather than categorical. This allows interpolation in order to obtain a predicted mean response of 50 inches. This concludes the first of two template examples in this video, the Catapult example. This paper airplane experiment is adapted from the article Teaching Taguchi's Approach to Parameter Design by Sanjeev Saran, Quality Progress, May of 1997. To open the paper airplane example file, click SigmaXL, Help, Template Examples, Taguchi Examples, L9 4-factor, Paper Airplane. If you wish to start with a blank template and populate the values like I'll be doing in this video, click SigmaXL, Design of Experiments, Basic Taguchi DOE Templates, Taguchi L9 3-level 4-factor. The response is distance of flight in inches. Our goal is to maximize distance, so we will maximize the signal-to-noise ratio by selecting SN, larger is better, from the list. The inner array controllable input factors used in the study are paper weight, 1 sheet, 2 sheets, or 3 sheets, design, design 1, design 2, and design 3, paper width, 4 inches, 6 inches, or 8 inches, and paper length, 6 inches, 8 inches, or 10 inches. The uncontrollable factors are launch height, launch angle, and ground surface. The outer array displayed here was created using an L4 3-factor design, but is not actually used in the calculations. The distance values are entered into the outer array of the L9 as yrep1 to yrep4. Scroll to the right to view the calculated statistics. Since there are no interactions, we will focus our analysis on the main effects plots for signal-to-noise ratio and mean distance as done in the paper. Scroll right and down to view the main effects plots for signal-to-noise ratios. The optimum settings to maximize SN ratio are paper weight equals 3, design equals 2, paper width equals 6, and paper length equals 10. Scroll left for a look at main effects plots for means. I'll adjust the axis for a better scale. The optimum settings to maximize the mean are paper weight equals 3, design equals 1, paper width equals 6, and paper length equals 10. Commenting on this difference, Sarin states, Factor B. The factor of design, plane built using design 1, was superior based on the mean value. Based on the average SN ratio, however, the difference between design 1 and design 2 was marginal. When there is disagreement between the level that optimizes the mean value and the one that maximizes the average SN ratio, it is usually recommended that the average SN ratio be given priority. This is due to the fact that the Taguchi approach focuses first on selecting levels of controllable factors that reduce variability. Bringing the process on target is a secondary objective. Thus, according to the Taguchi approach, design 2 should be recommended. But as a matter of practicality, design 1 was chosen, since it results in significant improvement in the mean value, while sacrificing the SN value to a relatively lesser degree. We will compare the two settings using the predicted output calculator. Scroll up to the predicted response calculator. Enter the values shown. Now, change the value for design to 1. As noted by the author, depending on the priority given to mean or signal-to-noise ratio, one would select design 1 or 2. In either case, confirmation runs need to be performed to validate the experimental results. This concludes part 2 of the SigmaXL Basic Taguchi Design of Experiments Templates tutorial video. For more videos, visit us at www.sigmaxl.com or join us on YouTube. Thank you for watching.